We're ready for the first lecture of this video set here of section 1.5. We're going to pick up where we left off on class on Tuesday. We're talking about limits. Remember that limits are we're looking at what's happening to the output variable as we manipulate and move the input. We saw in the other examples some limits that do exist, and what we're going to look at here are limits that do not exist and the ways that happens. One way is our two different one-sided limits. So what we're looking at is, suppose that we have, we're looking at something of 3 and we're approaching 3 from both sides. And again, remember that's a requirement for a limit to exist, is that we're approaching from both sides. And as we do this, one part of the graph looks like this, and the other part looks like this. Now, one thing that is happening here is that as we approach 3 from the less than 3 side, our input values are getting closer and closer to 3, and our output values are approaching this value, or we'll call A. As we approach from this direction with values of 3 greater than 3, our output values are approaching this value, B. And what I want you to think of is that if you had your hands, and your hand here and your hand here, and you brought them closer and closer together, if one's up here and one's down here, you can't clap. So we want to be able to clap our hands. And if we can clap our hands, then these are going to the same place, but in this case, they are not. Okay, so that's one way that we have that limits do not exist. They go to two different one-sided limits. So from one direction to the other, the output values do not allow us to clap. The other one is somewhat similar, but not exactly the same. But this is, again, we'll take our good old 3 again. And let's say as we come up to 3 on the input values from this direction, our output values are doing something like that. And then as we come up from this direction, maybe they're going in the same direction, however they never touch. The output values are getting larger and larger and larger. Perhaps though it's going down. So we have the situation that we are not able to have these. We can't clap. And often, as you recall, maybe in former mathematics, we have what we call a vertical asymptote. So these can go in the same direction. They can both go down. One can go up, one can go down. The other one is that we have some values that we say oscillate between two fixed values. So for this one, for instance, we'll take our good old 3 again. We might have, as we come up to 3, we might have values that do this. They go down here and here and here and here, and they keep bouncing back and forth, and the same thing happens over here. They just keep bouncing back and forth. They never settle on any one value, so they oscillate between two fixed values, and therefore there is no limit. These are limits that fail to exist. We have then a statement that says the existence of a limit. So we'll highlight this because it's an important statement here. The existence of a limit, if the function f is a function, and c and l are real numbers. Now let's go back and review this again. What we're talking about is, this is looking at the output values of our function. If as the input, and these are inputs here, as the input values go to some predetermined destination that we have chosen or is chosen for us, the inputs approach that value, what are the outputs doing? And if the outputs are approaching some given output value, then we say that the limit exists. Notice we say also here it's from both the left and the right. Both left and right limits. That means that we need to be able to come up on values that are less than the destined value of the input and greater than. Okay, well, let's take a look at an example of a problem here. We want to use the graph of this function. So what we see in black, all the dots and everything, is a function f of x. To identify the values of c, now this is referring to that, some input value here, for which the limit of the, and this would be the limit of the output values, exist. Explain why. So I want you to take a look at that. I want you to notice that you've got a closed dot here with an open dot, and let's just review, what does the open dot represent? We did this on Tuesday. It represents that it is not existing here. Okay, so there is no value right here, but there is a value there. Here's a point here. These lines here mean that it's going down, and it's going to infinity. They keep going down, down, down. Open dot, take a note of that. Closed dot. We want to know for what values of c the limit exists. Now let's take a moment here. Let's just consider some. Let's take a look. The limit as x approaches 0 of f of x. As we approach 0 from the from the greater than and from the less than side, do we say that the output values are going to the same place, or going to the same value? Could we clap? If we go up from here, our hand would end up here, and our right hand would end up there. And so we would say that at 0, the limit does not exist. That's what D and E stands for, does not exist. And I want you always, if you use that abbreviation, I want you to tell me why. And the reason is we have two different one-sided limits. Okay? Two different one-sided limits. So identify the values of c for which the limit exists. Well, definitely not at 0, so we can't use 0. Let's take a look at, this appears to be -2 right here, so let's take a look at the limit as x approaches -2 of the function. Do we think the limit exists? Now there's something interesting happen here. Is there an output value when the input is -2? And because this dot is here, the answer to that question is yes, there is an output value. However, as we approach -2 from the less than -2 side and then from the greater than -2 side, the values of the output are going down, 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 down. On this side, they go down, 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 down. And so is there a limit as we approach? And because these keep going down, the answer to that is no. The limit does not exist. And now I want to know why. And the reason is that because the output values are going to -infinity. Now there's a little bit of a disagreement between me and the author of our textbook. Because the author of the textbook, you might find that their answer says the limit as x approaches -2 equals -infinity. The reason I disagree with that is -infinity is not a number. It is a destination that we can never achieve. We can never get to there. It's just an idealistic destination out there. The limit does not exist, and this then is the reason why it does not exist. So you're going to need to remember this for the quizzes and the tests that we have, that I'm going to require you to give me a reason why, to state that it doesn't exist, and give me a reason why. Okay, so now it says the limit as x approaches c, we've found two values for which it does not exist, at 0 and at -2, but is there any place else that the limit does not exist? Well, you might be tempted to say -4, but let's take a look at that. The limit as x approaches -4 of f of x of the output values, the limit of the output values. Let's see here. As we approach negative 4 from the less than negative 4 side, we're coming down this arm, and we come down to here. If we approach negative 4 from the greater than negative 4, we're coming up to here. If one of my hands is going here and the other one is going here, could I clap, understanding that I can get as close to negative 4 as I want? And the answer to that is yes, it would. It does exist. The value of the function is not there. It happens to be down here, but the limit is going to here. So the limit, and I'm going to just come over here and look at this, the limit of those output values is 2. Now, it says to identify the values for which the limit exists. We have found one where it exists. Are there others? Actually, there are many, 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 many others. Anything along the input axis is going to give us a limit except at 0 and negative 2. You know, if I said, well, I want to find the limit at 5, I want to do that. Could I do that as I approach from 5 from the less than 5? I'm going up to here. And if I come from this side and coming down, could my hands clap if one was on the one side of that and one on the other? And the answer is yes. So, you know, we can have this to be a limit for everything except. So we would have to say this: the limit as x approaches c of f of x exists for all c not equal to 0 or not equal to negative 2. And that would be our answer then. Okay, continue to take a look at that, and we're going to go on then. Take a look at the next one. On this slide, we're looking at some properties of limits. And we're going to talk about these in detail. I don't want to get too much because I see my time is getting close to 15 here. But let me just start this and then we'll pick it up in the second session. Keep in mind that when we have the limit of b as x approaches c, we are talking about the limit of the output values of the function. So the first thing we have to say is, well, what is our function for this? And our function for this one is going to be the function f of x equals b. Now, b stands for any constant, and so it could be something like f of x equals 5. If that's true, then I would have a horizontal line right here, and no matter what value I would choose for the approach on my inputs, no matter what I do, I'm going to be coming up to and having that value of 5. And so on a constant function, the output values are going to be constant, and they're going to be just equal to b. The limit of those would be equal to b. Now let's take a look at this one. This function is something that I'm sure you recognize, f of x equals x. We can look at a graph of that. It's supposed to be a straight line there. And as a straight line, if I look at c and approach it from both sides, I have a point, and that corresponding output is going to be whatever this is. It would be f of c. And so and since f of x is equal to x, f of c, it would be simply equal to c. And so I'm going to do what we call a direct substitution. I'm going to stop this, and we will start the next session in just a little bit. This is part 2 of section 1.5. We're looking at properties of limits, and we're down to our third property here. We know that this says let n be a positive integer, so we are not going to look at x to the 1/2 power or anything other than positive integers. So it would be x squared, x cubed, x to the 4th, and so on. One thing that I want you to take note of is, especially on these two, what we're doing is what we call direct substitution. And we're going to try to do everything through direct substitution of the destination, the input value into our function. So if we look at this and we're letting the inputs go from x to c, or x approaching c, and our function is f of x equals x, let's say x squared, then f of c would be c squared, and can be any real number, any positive integer rather, and so in this case I chose 2. So again, we're using a direct substitution. Now, this one is very much like the others, except we have to be extremely careful that if the root index n is even, then we must have a radicand that is positive. You know, if we're looking at f of x equals the square root of x, and I try to use a value of, you know, f of -4, for instance, I'd have the square root of -4, which now is not a real number, and we are going to stay in the real number. So this would not qualify because this value is not a positive quantity, and so we would have to be careful about things like that. Again, though, notice that if we have a radical, if our function is a radical, and I chose the square root, it could be cube or fourth or fifth root, whatever, it is again this direct substitution. Okay, that is going to be something that we are really wanting to see happen in our problems, and we have to do a little work sometimes to make it do that, but we will be able to. Let's go on. We're going to do a lot of looking at properties and statements that help us out, and so bear with me as we go through these. Here we have the operations with limits. We are looking now at two functions, and we have function f of x, and we say that as x approaches c, the limit of the output values is L. And we have another function, g of x. As x approaches the same input value of c, the output values of g now are approaching this output value of k. We're going to see this type of statement for a lot of the work we do this semester. So we'll do our best to get through this with the limits, and then we'll repeat it over and again, and it will be hopefully more understandable as we go through this. One thing we need to talk about is this thing called a scalar. A scalar multiplier is this value b. A scalar multiplier is a factor that we multiply to something else. So we have here our function f of x, and we're saying that if we have some factor, some multiple of that function, and we know what the limit of that function is, then we also can just use the multiplier to the limit. So let's say we have f of x is equal to, let's say f of x, we'll just say x squared. If we said 4 times f of x, we would have 4x squared. And so if I'm looking at the limit as x goes to 2 of x squared, I would have 2 squared is 4. If I have 4 times that of the function, I'd have 4 times the quantity of our limit. The sum or difference. We look at those a lot. We don't even think about having it as a sum or difference, but let's suppose that we've got h of x is, let's say, x squared plus 2x. What we really have is a function f of x, which is x squared, and a function g of x, which is 2x. And when we add them together, we talked about creating new functions out of old ones by adding them together. This is an example. H of x would be f of x plus g of x. We have x squared plus 2x. This says that if this is the case, as we have here, then the limit of the sum of two functions is the sum of the limits of the two functions. So if I know the limit of x squared as x goes to some value c, and I know the limit of function g as x approaches the same destination, my inputs go to the same place, then I can just take the answers, the limit of this plus the limit of that, and I would have the limit of the sum of those. So I can take any function and break it into multiple monomials, evaluate each monomial individually, and then know the limit of the original one. Well, the same thing happens for product. The limit of the product of two functions is the product of the two limits. Quotient, same thing. The limit of the quotient of the two functions is the quotient of the two limits. But we do have to be very careful that we do not have a denominator that's equal to 0. So with that one exception, we are going to be able to apply the same rule. Same thing with power. The limit of a function to a power is the limit to a power, and the radical of the limit of the radical of a function is the radical of the limit. Again, being careful that we always have a positive quantity in there. Okay, again, this is just trying to explain some of the ideas, the main parts of limits. We're going to get into working these and applying these, and you're going to see some the ways that we do this, and it's really not as complicated as it may appear right now. Okay, here's one of the statements that we really like. The limit of a polynomial function. Now, as long as we are talking about a polynomial, remember a polynomial are, examples of polynomials are things like x squared plus 3x plus 4. We could have 10x to the 7th minus 3x squared plus 2. Anything of that nature is a polynomial. Look what happens here. If I have a polynomial and I have x approaching c, what's the limit of the outputs? This again is where we have what we use direct substitution. All we have to do is directly substitute this value c into our function. We like that. We don't want to have to work too hard. We like that to happen. Okay, well, let's look then at some examples here. Determine the limits as indicated, what we have here, and what I'm going to put down is we want the limit as x approaches 3 of f of x plus g of x. Okay. One way to do that would be to say, well, that's the limit as x approaches 3 of, and I'll just put 2x plus 5 in here because that's f of x, plus x cubed. Now, this is a polynomial. We just saw that as a polynomial, we are able to use what we call direct substitution. We also could say that at this point we have the sum of 3 different polynomials, and we just saw on 2 slides ago that we can use direct substitution. So we have 2 times 3 plus 5 plus 3 cubed there, and this would turn out to be 38. Now, we haven't done anything with the inspires, and I want to make sure that that we are able to do some checking of our answers. So let's take this. Let's go home and pick up a new document. And if it says, "Do you want to save?" your response is always no. Let's pick up a calculator here, and we're going to start with go to Menu, go to Actions. And we're going to define a few functions. We've got 2 actually, f of x and g of x. But we're going to define them as f1 of x. And let's see, f1 of x was 2x plus 5. And press enter. And then we're going to define another function. If I can spell this right, there we go. f2 of x. And we're going to define that as our g of x over here, which is x cubed. And we're going to use the caret there, and x cubed. Okay, and press enter. Now, what we want to do is to combine these two functions using the limit. So let's see where that limit template is. I think we saw this on Tuesday. If you're on this model, if you look right here at this key, I've got a template palette, and in the third row right down here is the limit template, and we're going to have as x and then tab. As x approaches 3, and tab and tab. And now instead of typing this again, we can say f1 of x. Remember, when these letters turn bold, that means that it's a reserved name, and we just reserved it up there. Move the cursor out from the first set of parentheses, plus f2 of x. And if our answer that we computed is correct, it should be 38. Let's see what happens. And it is 38. So we have verified our answer. Okay. Now another way we could do this would be to say, well, what's the limit as x approaches 3 of simply f of x? That'd be the same thing as saying the limit as x approaches 3 of 2x plus 5. Again, that's a polynomial function. I can use direct substitution, and we have 6 plus 5 is 11. My other function, though, is g of x. So I say the limit as x approaches 3 of g of x. That's the same thing as the limit as x approaches 3 of x cubed. And that would be 3 cubed, or 27. And if I add 11 and 27, I do in fact get 38. So 11 plus 37 or 27 rather, equals 38. Now let me call your attention to something, because showing me your work properly is very important. Remember that when we take the limit, this part of it right here tells me that what I need to be doing. It tells me that I am looking for what happens to the output values. I have to keep repeating that statement until I use direct substitution. Once I use direct substitution, I'm done. I do not, in fact, it would be improper to write that again. Okay, we can do the same thing with f of x times g of x. And our answer would be with the limit as x approaches 3 of f of x times g of x. That would be the limit as x approaches 3 of 2x plus 5 times x cubed. And what I would need to do here then is to, because it is going to be a polynomial, I can say that that's 2 times 3 plus 5 times 3 cubed. Let's see, 6 plus 5 is 11 times 27. That should be 297. We're going to check that to be absolutely certain. So I would do the limit. And I'm just going to go back here. And time is almost up. I'm going to stop this. Back up here. This is lecture number 3 of this lesson here. So I'm going to come back over here, and I will delete that and do a multiplication instead. And my answer is 297. Now, if we take a look at the third one, and that would be the limit as x approaches 3 of f of x divided by g of x. The only thing I have to be really careful about is the denominator. Is it going to be turning into 0? So let's take a look at that. This is 2x plus 5 divided by x cubed. If I use 3 in a direct substitution, would that be 0? And the answer, of course, is no. So I can use a direct substitution on here, and my answer would be 11/27. Okay, so we can use those direct substitution to our advantage. Let's go on. By the way, at any point, if I seem to go too fast, you can always stop this, pause it, rewind it, read it, and listen to it again. So please use this to fill in any gaps if I seem to be missing something or you missing something as I go through them. Okay, let's look at this. It's called the replacement theorem. This is one that we're going to be using a lot of also. We want to use direct substitution, but sometimes it's impossible. Okay, what this is saying is that if we have a function f of x and a function g of x, and keep in mind what we're saying is that the output of function f is equivalent to the output of function g for all values of the input except at that value c. If the limit of g of x exists as x approaches c, and the limit of f of x also exists, then the limit of f of x is equal to the limit of g of x. If the outputs are equal and the limits exist, then the limits are also equal. Now, what that allows us to do is this. Let's take a look at these problems. And let me do a little house cleaning here. We're just going to pop that over into a new one there. Give ourselves a little more room here. Okay. What we have is the limit as x approaches 1 of a problem 1 divided by x plus 4 minus 1 divided by 4 divided by x. I could replace x with 1 and have an equivalent problem here, but what I'd like to do is to be able to simplify this in a way that is going to help me get the answer possibly a little easier. So here we go. I'm going to take the limit as x approaches 1. I'm going to leave this x down here. And I'm going to just, remind myself that I could have that as x divided by 1 if I wanted to. Okay, in my numerator I have two fractions that have unlike denominators. I am wanting to use the same denominator for both of those, so I'm going to choose for the quantity x plus 4. That means in the first fraction, I need to know what can I multiply with this denominator so that it is exactly the same as my lowest common denominator. And I would need to multiply that by 4/4, so I have 4 up here, minus, and then in my second fraction I want to do the exact same thing. And in this case I need to multiply this denominator by the entire binomial x plus 4, and so I end up with 1 times x plus 4 and then 4 times x plus 4. So I have x plus 4. Okay. This is going to be equivalent then. The next step would be the limit as x approaches 1. Let's see if I can get that a little better here. I'll try that now. There we go. I still have my x down here, and that's x divided by 1. My numerator now, I've got two fractions. They have the same denominator, so I'm going to now combine those fractions. And if I combine them, I have the 4 from here. Keep in mind, I am subtracting this entire numerator. This is a common error. This is going to be negative x. Take the opposite of the 4, negative 4. When I look at this, and I look at this numerator here, I see that the 4's cancel. So I'll go ahead and simplify that. And I have the limit as x approaches 1. I still have my x divided by 1 down here. My numerator is negative x divided by 4, the quantity x plus 4. Okay. The next step would be to think about how do I divide by a fraction, and I believe we've already looked at that in this class, x approaching 1. So I have negative x divided by 4, the quantity x plus 4. That's this part right here. And if I divide by a fraction, I can multiply by its reciprocal. Now, if it helps, I'm going to put that inside brackets so that I can see that the limit of all of that is what I'm considering. Okay. I also see that I've got a common factor in the numerator and denominator, so I'll eliminate those. And I end up with the limit as x approaches 1, negative 1, because that's what's left here, times 1. Right there is negative 1, divided by 4, the quantity x plus 4. Now, because I was approaching 1, I could have used direct substitution from the very beginning, but I wanted to illustrate this whole process of finding a common denominator. So this primarily was here to show us that. At this point, I'm going to now do the direct substitution. I no longer have to write my instruction of that. So I have 4 the quantity 1 plus 4, and I end up with negative 1 divided by 4 times 5, or 20. So my answer would be negative 1/20th, which means that given this function, as x approaches 1, my output values of this entire quantity up here, my output values are approaching negative 1/20th. Okay, let's go on to our next problem. This one is a little more complicated. Complicated in that I cannot use direct substitution. Let's take a look at that. If I try to put 1 in for t, notice that this denominator is going to go to 0, and I cannot divide by 0. So here's where I'm going to definitely need to do some other work on this. So as t approaches 1, I have my denominator of t squared minus 1. My numerator, I think I can factor that, which I can, and that will be t plus 2 times t minus 1. And while I'm at it, we might as well factor this denominator. And of course, you know, you've done this many, many times over, that denominator is going to factor into something like t plus 1 and t minus 1. Now remember, we could not substitute 1 into, use direct substitution because it made the denominator 0. What I'd like to do is to eliminate that problem, and by factoring I can factor out or cancel out some factors, t minus 1, leaving me with the limit as t approaches 1 of t plus 2 divided by t plus 1. I still have t in the denominator, but can I now use direct substitution? Again, I just have to avoid the denominator of 0. So if I have 1 and in my numerator I have 1 plus 2, my denominator would be 1 plus 1. My answer would be 3/2. Could we use our Inspire to do that? Exactly in the same way we have been. I'm going to go back and look at the other, our gray model. To get to the template, it would be Control on the multiplication, pick up the limit, and now we have t. It's okay to use t. As t approaches 1, tab, tab, and we're going to put in a fraction, and we want t squared plus t minus 2, and that's divided by t squared minus 1. Check your answers as you go through. There's no reason to have a wrong answer. We want the answer of 3/2, and we get the answer of 3/2. Okay, so again, we're going to use our Inspires in many ways. One of them is to check answers. Okay, we're going to start the next problem and see how far we get on it. For now, let's go on the gray one. Let's go home, pick up a graph page, and let's see. We must have defined some functions before we did, and we don't want any of those. So we're going to define a new function, f of 3, or f3 rather. And it's going to be the one we just looked at, so we're going to type in. Now remember, we're going to have to use x and not t, and so this is going to be x squared plus x minus 2. Again, remember, we have to use the variables that are given to us, but when it comes to the graph piece of it, we have to use x. So we'll press enter. We're saying that as x approaches 1, so here's our 1, as x approaches 1, our output values are approaching 1/2. Does that look like, as we approach, as the inputs approach 1, that we would have a 1/2 there? So in order to make a stronger case, we'll go in here, we'll do points and lines, we'll do a point on, we'll put that point there. I'm going to hover over the input value, press enter twice, backspace delete, put a 1 in there, and let me try that one more time for us before time gets away from us. And why does it say that? It's an interesting thing there. We're going to have to check on that, but we're not going to do it now. We're going to do that in the next session. So as I pause this, let's think about that as you move on to the next one. Figure out why it says that you cannot change that. Let's go back and look. We said that if we put 1 into our denominator, it would become undefined. And so sure enough, we cannot do that, and the graph is not going to allow us to do that. Now remember, what we can do is to make it appear that we are as close to that as possible. One way would be to write 1.000001. Just get slightly greater than that, and we have then at the point 1, 1.5. Now keep in mind though, you know from your work, that if you have a dot on a graph, that means that that point is included, is a part of the graph, and we know from our work that that point in fact is not. Now some of you, you're going to do all this work on pieces of paper and hand it in, and you're not feeling as comfortable as others using Inspire, and that's perfectly okay. I don't expect everyone to do this, but for those of you who would like to continue to work and put this on your paper, put this on the Inspire, because you'll want to turn this file in as evidence of your work and not have to copy this on a piece of paper for a quiz or a test. Let me show you what we can do. You know that that point should not be closed in, and we need an open circle. So let's go to Menu, go to Actions, and come down to Attributes. Again, Menu, Actions, Attributes. And when we do that, we're going to take the cursor and we're going to go to what says Point On. We're going to change the attributes of that point. Press Enter, and that opens up then a menu that if you use the right or the left, you can get to various ways of representing that point. And so as long as I find something that has an open dot, I'm going to press Enter, and that now is an open dot. I'll press Escape to get out of that, and now I can show that at that point, as I approach 1, the inputs are going to go to 1.5. I'm going to save this for our document here and put it in our notes. Okay. Okay, looking at this problem, on first glance it can look a little more complicated than it needs to, but let's just kind of break it apart. First of all, instead of using X, we're using delta T. Delta stands for change of, so between T, a value T such as time, and another time, the difference between those two T values, we want the difference to be 0. So in other words, one value of T is approaching another value of T until there's almost no difference between them. We have T plus delta T, that quantity squared. That's a binomial. We're going to square it just like we would in the other binomial. Minus 5 times the quantity T plus delta T, and minus T squared minus 5T. Now, with delta T, think of it just like you would another variable. You cannot divide by 0. So here's where we need to rewrite this function so that we are able to actually use direct substitution. So let's get started with this. Just take it a step at a time. We have the limit as delta T approaches 0. Put that whole thing down here. Here's my delta T. And let's take a look at this squaring the binomial. You know, if you use the FOIL method, you know how to do that. So it would be T squared plus 2T times delta T plus delta T quantity squared. Then we have minus 5 times this quantity, so this is going to be minus 5T minus 5 delta T. And then we have minus this entire quantity. So again, remember to distribute that negative all the way through. Negative T squared plus 5T. Now at this point, I'm going to go back and see if I can erase those parentheses because we really don't need them in here anymore. And I'm also going to consider, are there any terms that I can cancel out? So here's a T squared and a negative T squared. Here's a 5T and a negative 5T. And I'll look at it. This is 2T delta T squared, negative 5 delta T. There's nothing more that I can factor out or cancel out. So now I'm going to look at this as the limit as delta T approaches 0. And if I take a look at the remaining terms, I have 2T plus delta T. I have delta T squared and negative 5 delta T. Each of those has a factor of delta T. So if I factor out a delta t from each and every one of them, I would then have the statement. Now, when I have the statement, now I consider, again, what was it that kept me from using direct substitution? Yes, it was putting 0 into the denominator. Now if I look at this and I consider, I have a factor of delta t and a factor of delta t, that's going to leave me with a factor of 1. And so my work now has reduced down to the limit as delta t approaches 0 of, notice I'm using the parentheses here because it is a quantity, a polynomial that I want to make sure I include in the entire function. Okay, any problem with direct substitution? No denominator. Nothing's going to be unreal. So now at this point, I'm going to go through and use direct substitution. Every place I see a delta t, I'm going to put a 0. Notice I do not write that notation again. Once I use direct substitution, I have taken the limit. I no longer have to write it. And my answer is 2t minus 5. Now that is an answer that we're going to be looking at in more detail in the next chapter, in fact the entire semester. Those of you who have had calculus before, you might recognize what we've just done, but for the rest of you we're going to leave the answer right like that. Now could we use the inspire to check our work? Yes. Doing the same thing that we have done before, taking a limit, setting the variable t, in this case t approaching 0. The only thing is, in place of using delta t, you're going to have to substitute something else in its place. So maybe it would help. Let's go back and let's look at this problem. We're going to go to the template again, and I can say, I want to say delta t. I can't use delta t. I've got to find something else. So let's use what would be a good variable here that all we need is a placeholder. So let's just use let's just use w. W, and we'll tab over approaches 0 and use a tab and tab. And if you look at this, we've got to now replace w in for delta t. So we've got a fraction. So let's put in a fraction. And I'm going to move that, see if I can get both of those. There we go. So that would be parentheses t minus w. Let me make sure I put a w in there. W, there we go. Quantity squared. And let's see, minus 5, and then a parenthesis, and we're looking at t plus w. And I see I have an error, so I'll go back and correct it. T plus w. So let me go back here. This should be t plus w there. Okay. So t plus w quantity squared minus 5t plus w, and then we have t squared minus 5t. So we have minus t squared minus 5t. All of that divided by w. Again, let's take a look at that. What I'm doing is, in place of delta t, I'm using a w. And so every place I see a delta t, I'm going to have to put a w. So w approaches 0, yes. T plus w quantity squared, 5 times the quantity t plus w minus t squared minus 5t divided by w, and we'll say enter. And it's undefined. It is as we would expect it to be an undefined value simply because it is dividing by 0. Now, if we go through and do the work on this that we have done on our paper, then we would have our answer of, in our case, it should be 2t minus 5. Okay, I do notice I've got something in error here. If we look back to this, notice this subtracting the quantity t squared minus 5t, and that's not what I have here. So I've used the up arrow to select that. I'm going to press enter. I'm going to backspace into here. I'm going to put a set of parentheses there to put that into a set of parentheses, and now when I hit enter, I do get 2t minus 5. So again, that should be why we the answer that we should have. So my error was not that anything except that I just forgot to put parentheses around there, which is going to happen to you also. So please, let's all of us be real careful about this. Okay. We've got a couple more items on this lecture note. I think I'll save them for when I see you in person. And I will stop this now. Please, again, go back and review this. Take a time to go over it a couple times if there's something that you don't understand. And I will see you on Tuesday for lecture. Have a nice weekend.